Welcome, everybody. This is C Pointers workshop by Night Hacks. My name is Max, and this is our objectives. So we're going to go over the C pointer syntax. There's going to be a few things we're going to need to get familiarized with before we dive into some of the more advanced topics like array structures and the memory allocation. And then we're going to understand we'll go into use cases for pointers, see some examples why pointers are important, and then we're going to do some practice problems or example problems if we have time in the end. All right, so first of all, why exactly the pointers are important, right? Or sorry, let's get this let's start out with this. So everything in C has or in any language for that matter, everything has a address, right? And the way we access the address of a variable is by this ampersand sign. And the easy way to remember is that ampersand kind of starts with a, and you can think of it as like address of this variable, right? So you do just ampersand and then the address of that variable. So we can do an example. Most of the examples we're going to do, I recommend you can follow this by just googling online C compiler. You just do online C compiler. And I recommend this first one, the GGB debugger. And just remove this. You can pretty much write code and then click run right here, and it's gonna the console is here that shows the output, right? So I already have mine open. I'll leave this one. So let's do a quick example of retrieving a address of a variable in C. Most of our examples today are going to be with integer types, but this is all applicable with all types. We'll also do some other data types as well. So I will create a variable x. It's an integer variable. We're going to initialize it to 5. And then in order to, first off, for just debugging, we're going to print that variable, right? We're going to say uh, x value, and we're going to say %z. This is just common C syntax for printing the variable. And we're going to see that x has a value of 5, right? Now, in order to access the address of the variable, like we already reviewed in the slide, it's the ampersand symbol, right? So for now, we're just going to do %z. This is a mistake, but let's just do the z for now, right? So ampersand x, and there you go. We have a address of the variable x. It's going to be just a random value, as you can see. You can never predict this because that's just the way memory works, right? You never know what the operating system is going to allocate for your program, so you can't tell what addresses are you going to have exactly. But this didn't crash, but as you can see, it gave me a warning. The reason for that warning being is that this the address kind of type in C has its own uh, letter here. It's actually P, right? P is for pointer. We're gonna also go into that a little later, but for now, just remember this: P is gonna be for all the addresses that you're printing to the console. Okay. So yeah, this is gonna print it in a nice like hexadecimal format. I'm assuming everybody's familiar with hexadecimal, right? That's just a convention how we print or differentiate the memory cells of the in the memory. And there's a nice little graphic in here. So we are kind of assigning. So here I'm using variable a, but it doesn't matter. So we're assigning value 5. It's a literal 5 to a variable a. And you can imagine this little memory. So this memory is really small, as you're gonna notice. It's only like 4 digits in hex, but usually memories nowadays they're like 64-bit, 32-bit. So but this is just a good like way to visualize it. So we're just imagining that the address at the cell like 4 hexadecimal gets the value 5, all right? And then once we access the address of that variable, we get its this value, which is this right here in this example, right? 0.0444. So yeah, pretty much that's it. If we just do a different type, this also works with other types, right? We can do double. Um, this would still work. We'll just need to change this to f. Um, yeah, so every variable in C has an address. All right, that's number one. Just remember this, okay? Number two, the same way we went from a variable to a address, we can do this the opposite. Okay, we can go from address back to memory and see call that process dereferencing. That's also something you just have to you're gonna have to remember. In future, it's gonna click in because the process of going that way is referencing and the opposite is dereferencing. But for now, just remember this. And the way we do this is by using the point or sorry, the star before the address. Okay, so you're gonna notice here we have ampersand variable name, right? In our case, it's ampersand x, or yeah, the variable is x, and then to get back to the value, we use the point, the star. Sorry. Let's also do an example of that, just to help us visualize. I'm gonna separate this with like a line like this. This file is going to get big. So x value, and we're going to say this is dereferencing, is, and we're going to do percent %d. We're going to switch back to ints just for, simplicity. So we do star, and then whatever's inside it has to be an address. So ampersand x, okay? And if we print this now, I'm forgetting the new line everywhere. Don't forget your new lines. All right. So yeah, as you can see, we 5 got printed. Is by the way, is this enough of a scale visible in the back rows? Right. Okay, good. So yeah, as you can see, 5 got printed because we dereferenced the address. Right. That's the opposite of getting the address. Is like getting back the what the address contains, right, or holds. So pretty much here, yeah, you can see the examples of that, A, B, and then this is pretty much what we did in that code snippet. All right, rule number 3. The referencing is not really useful if we're not like storing the address somewhere, because we can't just like walk around and write ampersand everywhere. We also need some way to like store the address of the of some variables in order for us in future to be able to reference it somewhere for our use, right? So there are pointer types in C, which is also something we have to just remember. Each data type has its own like a clone, not a clone, like a pointer type of that type. So for example, int has a int pointer, double has a double pointer. Okay, the way we denote those is with a star. This is going to be confusing because star is now being overloaded. We already saw that the star is used here to do reference. Well, that's how they design C. Unfortunately, can't do anything about it. You just have to, you know, remember, look at the use case. You could look at the context around how the star is used and see what's being meant. So in here, we're gonna create a pointer type of integer. This is how we do it, right? So int star, and then we'll call it y. And for now, we're just gonna say it's nothing, right? We're just gonna create it, and or we could do the other popular ways to do null, right? That's a clean quote unquote way to do this. But for now, since we're just starting out with this, I'll just create it like this, and this is the this is the pointer type of int, and we can, in theory, we can load it in with the address, right? So as you can see in the slides, the purpose of these pointer types is to store the addresses of the variables, right? So usually variables, they store literals, like in our case the x stores 5, right? This pointer type stores the address of any variable. In our case, it happens to be x because we are assigning it, right? And that's the way to do it. First, you you extract the address of x by doing the ampersand, and then you put it in y. Okay, and let's print whatever y has. Um, y, and then we're going to use the rule we just learned in the previous step, which is the referencing. As you guys remember, right? The way you get back from address to a value is by using the dereference operator. So we're going to say y dereferenced equals to, and then dereference y, right? So you're going to notice we just replaced whatever we had here, the address, with y, because y really literally does have that value, right? We're assigning it to that. And if we print, hopefully, yep, as you can see, y dereference is 5. So we're storing the address of this x, and then we're accessing it using this a whole different uh, variable y, which is a pointer actually. Same thing really applies with any other type. So if we create like a, or actually it's supposed to be like this, right? Just 5. So if we create a double, just for like demonstration purposes, I'm gonna show this real quick. Double of the same, double follows the same principle. This time the pointer has to be double though. Like I mentioned when I was explaining what the pointer type is, pointer type is kind of pointer type is an abstract thing. It becomes concrete when you give it exactly like what type it points to. For example, integer pointer, as you see here, and double pointer, right? And then one thing, you cannot assign integer pointers to doubles, to the addresses of the double, or vice versa, right? It has to be like one for one. Integer pointers are holding the addresses of the integers, and the doubles uh, hold the addresses of the double variables, right? So double pointer, we're gonna call it, or actually, we have to call this a, okay, because y is already taken. We're gonna call this b, and the other way to assign a pointer, we can assign it in place. This is called initializing. I'm sure you guys are familiar with that. We're gonna initialize the value of pointer b in place here, and we're gonna say it equals to a, and then address of a, right? Because pointers, once again, store the addresses of the variables. And now let's print it also. We're gonna say b dereferenced. This time it's gonna have to be f for float, right? Because it's a double. And then b dereferenced. We're gonna run. We're gonna get our variable 4 back. Sorry for that. All right, let's go next. So yeah, this slide we already covered in code, right? So we're essentially going through the whole workflow here of creating a variable and then creating a pointer for that variable and then assigning the pointer to the address of that variable. Just exactly what we did in code, right? And same thing for doubles. All right. And the way to visualize that, by the way, is through this graphic right here on the right. If you take a look, you're going to notice that uh, our variable a has an address of, for in our example, right? We imagine that this is hexadecimal 4 and it holds 5. The way to visualize pointers is that the pointer, right? It's also a variable x, and it also has a place in memory. But instead of getting a value, it gets the literal like address of a, right, of this variable, and that's how the dereferencing trick really works. Okay. And yeah, just to reiterate the many meanings of the star. On top of everything, there is also a multiplication, right? Uh, we can multiply literals with the star. We can define the pointer types with star, right? This defines a integer pointer. This defines the float pointer, and we can also dereference with the star. So please keep this in mind. Remember this, okay? Depending on what context the star is being used in. By the way, integer star y, right? Many people prefer to do it like this. Many people. So line 14 right here. Please take a look. You're gonna see a lot of code that's like this, okay? It's a little bit not intuitive to me, but feel free to use whatever you think is more understandable for you at this point, right? But for me, it's just easy to do this way is because it's an integer pointer, and then if you don't assign it to a value, next line you can by the way, let's move this up. Oh, sorry. Let's move this up, right? You can if you're not initializing it, the next line you can literally say, hey, this value gets an address. But if you do it like this, it's not clear, right? Star y, and the next line is just y, right? Why are we not doing star? So I just prefer it this way, but you do you, okay? Whatever helps you understand. Uh, all right, declaration versus initialization. I also covered this in the code snippet already. The There are two ways, right? You either initialize and then you either don't initialize and you just assign it later to a address of some variable. All right, so now let's move on to some of the more advanced concepts, right? The same way we can point to variables, we can also point to pointers, and the same exact tricks really apply to that as well, to that process. So yeah, the slide says before we were pointing to variables, now we're going to be pointing to pointers, and this is where the term dereferencing is going to become clear. Let's go into code, and we're going to create what's known as a pointer to a pointer. So we already have x, right? That's an integer. We have y, that's a pointer to an integer. And now we're going to have int double reference. Okay, so int pointer to a pointer. We're not going to call it is z taken? Z, no, z is free. Okay, we're going to use z for this, and this is now a pointer to a pointer. Okay, so we can even initialize it by giving it a value of an address to a pointer. Okay, please pay attention. Address, right? Not just the pointer value itself. This way, if we did it this way, it would really have to be like this, right? Because we're assigning a pointer type to a pointer type. But here, this is a double pointer, so we're going to be dereferencing this value in future. So we really need the address of that. And now let's check what happens if we dereference it once, right? So uh, z dereferenced dereferenced equals to. I'm going to use p for now. You're going to understand why in just a moment. And z dereference, right? Once again, here we're using stars to indicate that this is a pointer type. Here we're using a star to indicate that we're dereferencing. Okay. Um, what do you guys think this will print without printing? Like, let's be honest. Who wants to guess?
The address of the pointer.
Address of the pointer. Which one?
The other one.
The
Not Z.
the Y, right? All right. Awesome. Yeah, this is correct. Oh, I'm forgetting the new lines again. One sec. Yeah, so it printed the address of that pointer, and that thing, the address of what we just printed, is also a pointer. What do you guys think we can do next? What do you guys think we can do with this to do something useful with it? Can we maybe print the value of the previous integer, or rather, the value that we originally pointed with this value, right? How would you do that? How do you think? Yep, two pointers. Well, be more specific. To the references, exactly. So we do double star, right? So this is to the referencing, the referencing two times, and now we get five. Well, actually, we need to change this back to z, right? Because it's a decimal, z for decimal. Because z, well, not z, but this holds the integer type. So yeah, now we get back to the original value. The way now to think about dereferencing is you're kind of removing stars. Okay, the easy way to remember this is think of it as like a stack. Here you see you have a this is a data type. Okay, int star star. This is a data type. This is a integer pointer to a pointer, right? By removing one star, right, by dereferencing it, that's why it's on the other side, right? That's how you can like mentally remember this. By removing this one star, you get back a new type, which becomes a pointer type, right? Previously it was a pointer to a pointer, now it's a pointer. By adding another star, right, now you're removing this star, and now you're back with your original integer. That's the easy way to remember it. Okay. Questions so far? Everything clear so far? Everything compiles? Whoever is following? Okay, good. All right. That's one advanced concept. All right. Congrats. You now know one advanced concept. Yeah. So this is what we did, right? We played with like dereferencing many times, two times here, right? Um, so now a second advanced concept, and this is where it gets a little more tricky. Okay. So we can do pointer arithmetic with our pointer type. So the pointer type is when we printed it, we saw the hexadecimal, right? What if we wanted to, let's say, access the value of not this cell, but like the next one? The pointer arithmetic is here exactly to do that, right? It exists exactly for that purpose. So we can say +1, and the C compiler is going to be smart enough to know that we are that the type of this, because we already gave this variable a type when we created it, right? We said it's an int, and it's going to know, oh, okay, so this programmer wants to add one size of the integer cell, memory cell, and that way the programmer really means that he wants to, by this operation, he really wants to access the next cell in the memory, okay? And the way it does it is by typecasting. You've heard of typecasting, right? That's a concept that is actually, typecasting is used with other variables like integers and floats, right? If you do float plus integer, the integer is going to be casted to a float. Same thing here. You're doing a address type, right, or a pointer type plus a literal, and the literal is going to be casted to the size of that uh, reference type. Okay, let's do an example. So we have here. I'm not going to erase anything. I'll just reuse our pointer type y, right? So we have y address, and this is going to be p, right? Because remember pointer type, and then oh, actually we're going to do x address because this will. Actually, yeah, let's do y. Sorry. Um, all right, mini quiz. What is this going to print without printing it? If anybody can tell, what do you guys think? Any guesses? I'm printing. I'm saying y address, and I'm giving it y.
The address for X.
The address for x, correct? Yep. Just to make sure you guys still paying attention. So let's print it. There's gonna. Oh, there you go. There's an error. We're putting the new line after the string. Okay, so yeah, we got an address. Anybody wants to guess what happens if we print y+1 address? Anybody, please. So look at what this printed and kind of logically try to infer.
The address plus one more address, like the next one.
One more? Okay, good guess. Everybody agrees? So it's actually going to be +4 because if you remember the integer type, this probably was covered in like one of the first weeks. The integer type really has 4 bytes, right? So if I print this, this is going to be +4. Okay. Same thing with double. If I do a double, the double is on most machines. It's not precise. You cannot say, oh, double has exactly 8 bytes, right? It depends, but on most machines, double is going to be a difference of 8. So if I do instead of our y, I think our double version was b. So I'll do b+1. Now it's a difference of 8, right? Because it's hexadecimal, right? So 8 plus 8 is going to be like 16, and In hexadecimal 16, it becomes, it overflows, right, to the next, to the 770 question. Yeah.
So does each memory address store only one byte?
Yes. So it's so the question is, yeah, does the each memory address? Okay, so the cells in the computer, the memory in the computer is still interpreted in terms of bytes, but the program, when it like allocates the lines for your code, it uses the next 4 bytes for example, the integer. So yes, in the computer, it's going to be, each cell is going to be like 1 byte, but actually, for the int, the four of them are being used, right? So for
So
example,
so
yeah.
like right there is x0004. That's actually storing 4567.
Yes, correct. So it's actually showing this. I drew this. This is probably not the most accurate diagram, right? You are correct. In the reality, it's supposed to be 4, 5, 6, and so on, right? And since this is only showing the int example, right? This is the int, but the double would take like two of these cells, right? Because double is 8 of them. But yeah, you are correct. Each of them should be really drawn here. All right. Uh, all right, and here are some common types, right, on most machines. So decrementing and incrementing works the same way. You can also like go back. If we just subtract one, could always go back. This should print 60 now because we're going back. Okay, or sorry, not 60. Okay, now I guessed wrong. Okay, but it decremented by 8. Okay, and this should really be minus. Okay, good. Next, now a third advanced concept. Okay, this is going to be even more trickier. So you know arrays, right? Everybody knows arrays. Who can give me a definition of an array? Yeah.
Isn't it a collection of elements that are next to each other in order, basically? They're
Hmm.
accessible through a single point.
Correct, but one more important description of that is missing. What are you missing? Can you try to think?
Now,
What did she
each
miss?
element has
The same
the same
type. Correct.
type. Yeah.
Yes, that's precisely correct. And you're gonna, like, before this, it was a rule that they have the same type, but now you're actually gonna understand why they have the same type. Okay, there's actually a reason behind it. So okay, this is going to be something you'll have to remember. There's no like good first first time explanation for this. Array, the name of your array, right? For example, we have an array R, right? ARR. That's actually in itself, it's a pointer. Just remember this, okay? We're gonna see exactly why that works out. So let's go back into the code. It's a pointer to what though? Who can guess? Does anybody have like theories? First, oh no, you already covered this.
Yeah.
Gotcha. All right, cool, cool. Yeah, so he's correct. The array is actually a pointer to the first element inside that array. So let's see what exactly that means, right? We're going to create a new array. We're going to call it also R to be consistent. It's going to be an integer array. And this is a quick notation to uh, create an array, right? And if we did everything correctly, we should be able to print all the elements in the array. This is just for debugging purposes, for us to see that this really works, right? Everybody remembers this notation, right? This is for loop, and we're doing. All right. Why is it not print? Correct. Good catch. Who said that? Bonus points. All right. So 1 to 3, we got printed. We printed 1 to 3, so everything worked. We initialized our array as everything's correct. So now let's play with it even more. We're gonna print. We're gonna print. We're gonna say it's a P, and we're gonna say name of the array. All right. New line. I'm gonna say, so we're gonna say name of the array, and we're gonna print this R. And we're gonna see what happens. So this prints something, okay? Prints some memory address. Now, what we'll do is we're gonna print first element of the array, okay? And we're gonna say also P, but oh, sorry, not the first element, actually the address of the first element of the array. And we're gonna say, so the way to do it is ampersand, right? Remember, that's our first thing we learned, how to get the address of a variable. And same logic applies with like pointers, right? We just first we access that variable, and then we get address of that. So misspelled printf. You're gonna notice it printed the exact same things. Okay, that's just a rule. Okay, remember this. The name, the literal name of the array, is a pointer in itself, and it points to what? To the not the first element, to the address of the first element. Yeah, just to keep the wording consistent, right? All right. So, what is the implication of that? Can someone connect two to two together with this concept and the pointer arithmetic we discussed like a slide ago? Awesome, awesome. Yes, he is correct. So what he's saying is that we can use the fact that the array name is literally the pointer to the first element, and the fact that we have a pointer arithmetic that allows us to shift in between like the memory cells. We can use that to iterate through an array, right? And we're gonna do just that now. So we're gonna say, so the same thing we did here. I'm gonna call this in old school, and now we're gonna do this a fancy way. For int I equals 0, I less than 3, plus. For enough, we're gonna do percent %z, new line. So first, how do we print the first element? Can someone tell me? So array prints the address of the first element, right? How do we print the value? Star where? Front. And how is it called? This the reference. Correct. Awesome. Bonus points. This prints the first element, but we actually need to make it dynamic, right? So that it prints all of them because we're doing the for loop, right? Who can tell how we can achieve that? Plus one. Okay, where? Here, right? Plus I here. Without compiling, can someone tell me this will this work or not? Plus one? Well, plus one is just gonna do plus one four times or three times, right? But we need to this time it's 0. Second turn of the iteration is 1. Third turn is 3. So it is I. The first thing you said actually was correct. But is this in general? Is this correct? What do you guys think? Parentheses, exactly. So what we're doing here, right? We're saying take the address, add I to it, right? This is either 0, 1, or 2, and then we get a new address. So we're kind of getting a new address, and then we are dereferencing that new address, and not first dereferencing and then adding it, right? So the parentheses are actually important. So once we do that, and we forgot to also print, uh, we're gonna say this is fancy operation. All right. Oh, and this is gonna be regular operation. All right. So if you don't believe me here, it compiled the same, right? Two ways are exactly equivalent, and that is exactly why each element in the pointer has to be the same type, right? Because if we add I to it, the compiler needs to know, oh, okay, this is an integer. So I'm adding 4 bytes and I'm accessing the next element, right? Or this is a double in this case, and I'm adding 8 bytes now to access the next element. Okay. All right. There's that. Pointer arithmetic here. This slide is essentially talking about that. And yeah, we already did this, right? In our for loop, we just use I instead. First I was 0, then I was 1, then I was 2. And equivalent, the old school way, the way we all know, right? Okay, now let's try to understand. Well, this is cool, right? We can impress our friends by the new way we print the for loop or the array, right? But how we can actually use this and why is this all important? Anybody heard here about pass by reference and pass by value? Okay, good, awesome. So whenever you send a value to a function, what happens, right? Inside that function, you like do something with that value. The purpose of the function is to abstract that code away, pull that code away, right? That code away so that it's clean. And you do that type of work inside that function, and then you return everything's clean, all good, right? Well, inside that function, you mess with that value that you passed. For example, we're going to pass 3 in there, right? And we're going to modify it. We're going to make it equal to something else. When we get back, this all the modifications we did, they're not going to work because what we're actually doing is we're sending the value, we're sending the copy of that variable, okay? And we're gonna see that that's the case. So we're gonna create a new function. I'm gonna create the header for the function. It's gonna be a void function. We're gonna say pass by value, and the function is gonna be accepting an integer, and we're gonna say it's a val. Okay, we're gonna call it integer val. Here below, now we have to. Oh, sorry. Now we have to implement that, right? It was a void pass by value int val. So what we're going to do here is we're going to say value equals value times 2, okay? So this is going to be a times 2 multiplier function, okay? So we're going to call that on our variable x, or what was the initial variable? X, yeah. X is 5, right? So we're going to say printf. This is a shortcut, right? You don't have to really um, say, you don't have to create a new variable. You can just do it like this directly, or actually rather, okay. First you do have to pass it. Sorry, value, and then we're passing x, right? So here we're going to print x after the fact. So new x after function. Okay. I'm also going to comment out all of this. Oh, except for our x. Okay. All right. So x was 5 in the beginning, as you can see here. We passed it to our pass by value, and we can also, what we can do is print it here, right? Why not? Printf. We're gonna say x inside the function val. Okay. Now what is this going to print? What do you guys think in here? So we're passing 5, 5 by 2, 10. Awesome. And yeah, correct. Inside of the function, it did the multiplication job, but whatever we did didn't affect our real x, right, in the main. The reason for that is because we like I said, we're only passing the copy of that variable. We're not passing the address of that variable. But what pointers will allow us to do, and what the beauty of pointers are, is we can actually achieve changing this variable without having to return anything. So the workaround for this would be returning the new x, right, and then assigning it back to the original x. But what if that variable is huge? What if it's a big array, right? We need a way to like modify it without returning it. So a pass by reference is exactly that. I'm going to create a new function. It's also going to be a void. We're going to go call it pass by reference, and this is only called pass by reference and pass by value for like historic reasons. That's you're going to get used to it. Once you get like more experience with like references and the pointers. Well, references is another like synonym for pointers to clear up confusion. Okay, so the same way we're passing this value, we're going to pass it, but the only difference is going to be that this is going to be, now we're passing the pointer. Okay, or the reference to the integer, in other words, right? Pointer to the integer. We're going to do the same thing, but here we're going to dereference it first, and we're gonna multiply the reference version by 2, and we're gonna assign it back to that dereferenced memory cell. Okay, let's not forget to give a header to this function. Now we're gonna call pass by reference this time on x, and spoiler alert, this is not gonna work. Can someone tell me why? This is gonna crash. Why? Ampersand. Perfect. Okay, so he's really paying attention. Everybody, take example. All right, so we're sending the address. So this time we're sending a reference. And would you look at that, right? Now the new x after the I should clarify this. After the reference function, right? The this function, the reference function, now it's a 10, right? So the original x from this scope, and by scope I really mean like this function, right? That's just a fancy name for a function, right? In this function, the x was modified because we really passed the address of x and not the copy of x. And here's exactly why it worked. So when we pass the value, we just like imagine this box is the scope of the function main, and this box is the scope of the function double value, right? Because our here in this slide it's called double value. Okay, so we're passing. So in case of the pass by value, we're passing 5 to the function, right? But in the case of pass by reference, we're really passing the 0x0004, which is 4 in hexadecimal, right? So we're really passing the address of x, and we're saying, hey, dereference that address, get the value of x, and then in that address, so now we have the address, put back the value, the new value, and now the content of the address changed rather than the just the local copy that we were doing before. Okay, so this is also something you guys need to remember and pay attention to. Uh, this is a way to change the value of your variable in another function, or in other words, another scope, right? We call them scopes. And here we're passing just an ampersand x, right? We could also easily have said uh, int int pointer, right? Int star y equals address of x, and we could have done this. And just to differentiate, I'm going to say here in parentheses y, okay? So that we see that this actually now prints the new version. And this works just the same way, right? Y and the 10 is now changed. All right, awesome. So next, this is the main juice of the pointers, right? The biggest use case of the pointers is right here: memory allocation and deallocation, aka memory management, right? So there are situations in your program when you have to create an array, let's say, and we you don't know. Well, the computer doesn't know what's the size of that array. Okay, even you sometimes don't know what's the size of the array because the size may be given to you from outside, from the users of your program, right? For example, right, like a memory, like a network request. Some network request might come to your server, right? Let's imagine this is a server, and now it gives you the size of 5. Now you need to allocate the memory of 5, and you notice how I use the word allocate. That's the buzzword for this, right? Allocation of memory. In other words, we're telling the computer how much memory we need for this array. In other words, we're saying in other words, we're telling what's the size of that array going to be, right? And the way it happens is you call a little function that is given to you from the C standard library, and you give it the size of how much you want to the compiler to allocate, right, to your program, and it returns to you a what? Just try to imagine the situation, right? We want to allocate some block of memory. In some cases, it's going to be like a block of 5, right? 5 sizes of int. So 5 by 4, like 20, right? 20 bytes. In some cases, it's going to be like 40, right? If it's double that. Well, if you were to ask your operating system or like your compiler, right, to allocate that memory and somehow give it back to you, what would be the currency that it uses to give it back to you? What do you guys think? Any guesses? All right. Well, returning an array would be heavy. You would have to return every like element of the array. What if it's millions of elements, right? Pointer to what? Okay, but specifically to what? For example, right? To the memory address that the compiler allocated, right? Correct. But very it's correct. We're gonna count it as correct. Awesome. So the compiler, right? You call the function. You're kind of like making a phone call. Hey, give me some memory, like 20 bytes, and it's gonna return you the pointer that points to like the beginning of the place in memory where that 20 bytes that it allocated for you start. Okay. And this is exactly what the slide kind of explains to you. All right. So how do we exactly, what do we call, right? How do we make that phone call to get that memory? We're gonna need a function that's called malloc. Okay. What malloc is gonna do is exactly what we explained, right? It's gonna allocate some memory, and the malloc stands for memory allocation, right? M alloc. I'm calling it malloc. Probably it's not what other people's call it, but I like to call it that. But most people call it M alloc, right? Memory allocation. So you give it the size, it gives you back the pointer. Let's do that in an example, okay? I'm gonna comment out everything again. So for return 0. So we're gonna create a new integer array rather. Uh, And notice here, we're not just saying array and then like this, because this wouldn't work, right? We need to give it a size, right? 10. This wouldn't work, but we don't know the size. So what do we create instead? A pointer, correct? So this will be because we already learned before that the name of the array is not nothing else than just a pointer to the first element of the array. And we can leverage that. We can just create a pointer and call it r and pretend, hey, this is our future array. Right now it's empty, right? Nothing is here. That's because we're going to allocate the memory for it dynamically. And for this, for those of you who are following right now, go up and import the library stdlib. Okay, stdlib. This is where the malloc function lives. This is the function that we use to make the call to the compiler to allocate some memory. Okay, so go here and say r equals malloc memory allocate, and you give it the size of how much memory you want to allocate, right? Let's say that we have size right here. Size equals 10. We're going to say size, but you have to remember, computer thinks in terms of bytes, right? In terms of like data types and stuff. So we need to tell what we really mean by size, and we're going to multiply that size by size of integer. Let me explain what size of is. Exactly what you think it is. Size of gets you the size of a data type. In our case, what is this going to return? Any guesses? Four, correct. Yeah. So this function then accepts the number of bytes that you need to that you're requesting, and it allocates all those bytes to you and returns you a pointer, right? And we assign that pointer to our pointer variable r, right? Because we already declared it as a pointer variable. So we get that in return. Let's compile it just to verify it works. We're gonna say printf works, and I'm also aware that I'm making a major mistake, but I will get to that. Uh, Works. Okay, so works prints. Don't print it, guys, please. We'll get to that. Why we're doing that. So now there's one more thing you just have to like remember for now. Every time you are allocating memory, for every allocation you do, you have to match it with a deallocation. Because what really happens behind the scenes is that that memory gets reserved for you. It's like a VIP zone, right? Reserved for you. Nobody else can use it. And then you, once you're done with your program, the main function runs to completion. The program ends, but the memory is not released. Okay, the memory is gonna keep being like allocated and not freed. And then if you run your program enough times, in theory, right? If you run it, let's say 1,000 times, you're gonna allocate a lot of memory that you're not gonna be releasing, and now your computer has less memory to work with. So your computer would, if you have a 8 GB RAM, you would have now like a 4 GB RAM. Let's say you froze 4 GB of memory. The way to fix that would be to just reboot your computer to release all that memory, but that's a dirty solution. The clean way and the safe way to do it is to release the memory, and the function for that is free. This is easy. This is one naming that they really uh, got right. So this is easy to remember. Free function. So what that function takes is the pointer which was returned by the malloc, right? Conveniently, we stored it in r, in the variable r, so we just send it back to the free, right? And then we just have to remember to match every memory allocation with a free. Okay, if you don't pass nothing here, it's not going to work, obviously. So you have to pass the exact pointer that was returned to you here. Also, if you have like a different pointer, right? Let's say we call it second. And if let's say we just did some code here in our function, and at some point we just assigned this second to r, right? Freeing that will also work. Okay, this is also something that will come with experience, but you have to remember, because pointers, these are really just labels. The underlying pointer that was created here in the malloc, it was created once. You pass it here to the r passes it here to the second. Now we're just using, hey, label second holds that pointer, free whatever pointer is inside second, okay? But in our case, this is just for the demonstration, okay? I'm gonna remove it back. Okay, so now I print It again. Now it's clean. Okay. This is also in the slice, the free point. So you're gonna get access to the slice if you want to like get a cheat sheet of all of the things we're discussing here. The free function is here, and the example of the free function usage is gonna be in that next slide. Okay. So here we're allocating it, and here we're deallocating it. Okay. Free. Awesome. It would be nice if they called it dialog or something, right? But you know, whatever. Now the question is, how do we now populate this? Like we allocated some size for our array, right? So it's 10, right? Size here 10 times of size of integer. Well, now we just allocate it like we usually allocate our arrays. So we're gonna have a for loop, right? Int I equals y less than size, and then we're gonna say I plus plus. And for the demonstration purposes, we're just going to do I. We're just going to assign it to the same value as here, right? And then we're going to create a separate for loop, right? We could also do it in the same for loop, but just to make it clear, I'll keep it separate. This is the for loop for printing specifically. I'm going to say printf %d new line, and then ri. It works. We created a array. We dynamically gave it a size of 10, right? We didn't know it at the buzzword for this is compile time. We didn't know it at the compile time. We knew it at the run time. Okay, that's the word for that. But don't have to remember that. Okay, so we figured out. Well, in this specific example, it wasn't exactly at the runtime. We knew this at the compile time. But let's actually make an example where we will learn it in the runtime. So I'm going to remove this, right? Size equals 10. I'm going to remove this, and I'm going to instead make a print statement. I'm going to say please enter the size of the array. And you already guessed what we're going to do next, right? The good old scanf. We're going to request for d decimal, right? That's for int. And we're going to give the address of that integer. So size. So whatever user inputs is going to go into the size variable. And then once they do, this whole process is going to proceed. Okay. You're all familiar with this, right? The how to get input from user. Okay, so we're gonna run our nice little program. It's gonna ask us for the number. Who wants to do the honors? Give me the number. Random number. Three. Okay, let's do three. Enter. Boom. 0, 1, 2, 3. Right? Oh, sorry. 0, 1, 2. So we got array of size 3, and it's a zero indexed array. So 0, 1, 3 are 3 elements of that array. Now, let's do a mini quiz. Who wants to help me to convert this into the fancy way of printing the array? The fancy notation. All right, what are we doing? Okay, so I'm getting rid of what here? The brackets, right? What are we doing with I? Adding, okay. Parentheses, okay. Where? Where does it go? Before this one? All right, awesome. Good job. So this guy nailed it. Please enter the array. This time we'll do like 88. Now we got our 88 elements. All right, in a fancy notation that you guys learned. Okay, so yeah, important steps. I'm going to repeat that because that is important. Always remember to include your library, because if I remove this, spoiler, this is not going to work. It crashed, right? Because malloc is really coming from here, the mmalloc, right? And we're not including it. So it's complaining, hey, there's no malloc. What are you talking about? What is malloc? I don't know, right? Let's bring it back. Whoops. Oh, um, probably the fact that we're running it to break it is messing with me being able to like do anything. So now when this is how you know how malicious these types of errors are, right? When you're forgetting to include the library, when you're dealing with malloc, memory allocation, always dangerous stuff. Always be alert. Okay. So now everything works again. Three, everything works. All right, let's go next. Structures. How many guys of you know structures? But you're in C, intro to C. Okay. But you learn you know it from before, right? From your own context. Not from the class. Okay. Let me think here. Since you guys didn't cover it, should I cover it or not? Okay, so I am going to cover it because some of the people watching may be already familiar with it. But this is going to be like 10 minutes, and then we'll get to examples. But if you feel lost here right now, just don't worry. But I'll still explain it the way that it's going to be understandable. So worst case scenario is just know this concept in advance, like before covering it in the intro to C. Okay. So what are structs? Structs are structures, or structs in short, are a way for us to create our own custom data types. So for example, if I want a data type, as you can see here, right, in the code snippet, if I want a data type user, that is not an integer, that is not just a primitive type, but my custom type, right? It has a value of int ID, right? So I'm imagining that my type user has an ID and like a, well, we already learned from this session that this is nothing more than a pointer. And in our case, the pointers can be really used as arrays, right? So we're doing friend ID list, and we're saying this is going to be our dynamic array in the future, right? So this is our type user, and this is a fancy notation how to create a structure by using the type def keyword. We can also do it without type def keyword, and it's going to be just struct user. And let's do that exactly that in the code right now, okay? So we will just comment out all this for now. Let's create a structure. Structures are usually created outside of your functions, outside of your all of the functions, right? In this global scope, I'm going to say struct user. There's always a semicolon in the end. We're going to say, what was it? Int id and int pointer friend id list. So, for example, this user has friends. We're like imagining this is a little part of our, let's imagine a social network site or something, or, you know, social network, right? And we have users with IDs and their friends. We can also store their IDs. It can be a list, okay? So, yeah, we're declaring the struct. For some reason, it's not coloring. Well, I'm sure it's correct. So let's go down here. And the way we create an instance of that struct is by saying uh, struct user one, right? And then we're gonna say user1 dot id equals 1, and we're gonna just print it to make sure it works. ID equals %z. I'm gonna say user1 id. Awesome, it worked, right? So in short, that's just a brief introduction to structs. Just one comment I want to make is, like I said, the fancy way to do it is by using the type def, right? You don't have to memorize this. It's just a thing that makes it look a little cleaner. We're going to add user here at the end because that's the rule with type def, right? And what this does is it just allows us to make the struct here look nicer. We're removing this, right? So now it's just a whole type that we define. Type def stands for define, or I misspelled it, type def. type def stands for type define, right? And we're defining our new custom type user. Okay, custom structure type user. Don't worry if this is too much for now. The reason why I brought it up is because let's run it. Everything still works. The reason I brought it up is because we can also create structures for these pointers for these custom types, and we can also go further. We can have pointers inside those custom types. As you can see here, this array, oh sorry, this pointer here can be used as an array with our new memory allocation technique, right? That we learned. So if we just go here and we say, where was that? If we say user one friend ID list equals, and we're going to say malloc, and let's give it a size of 5 users for now, times size of integer, right? Because our field here is integer, int friend list. Um, so for every malloc, we have to also do a what? Free, correct. A deallocation. And this is a little trickier, right? What exactly do I free here? What do I type in inside here? Because remember, the malloc returned us the pointer. We assigned it to our friend list, right? Friend ID list. Now that same pointer that was allocated with malloc, we need to pass it to free at the end of our program. Oh, sorry. So what do we pass here? User one dot friend ID list. Correct. Awesome. Okay, so now our program is memory free and sorry, memory leak free. And the name for that, for the issue that I described before, I'm not sure if I said it. The name for that is memory leaks, right? That's what they call it when your memory gets too reserved in your computer and you're forgetting to free it. The term for that is memory leak. Okay. So yeah, let's print it. Everything still works, and we're allocating an array of 5. So now, in theory, this now becomes an array because we gave it a block of 5 times size of int, which is 4. We gave it a block of 20. So now, in theory, we can iterate through this array for int I equals 0, I less than 5, right? Because we used 5 in here, and then I plus plus. So we're gonna treat it as a regular array. We're just gonna do the old notation. We're not gonna do the fancy way for now. And we're gonna say that each array element gets the value of that value I. Okay. Run it. Or we're not printing it, so let's create a separate for loop to print all these values. F %d ID of friend we're gonna print the number of each friend %d equals to %d new line. Okay. Awesome. Okay, we're missing an I here. So this I corresponds to this D, right? Number of the friend. This ID value in the array of IDs correspond to this D. So let's print it now. So ID of friend 0 is 0, ID of friend 1 is 1, and so on, okay? So we dynamically allocated the array inside of the structure, right? This is the whole point why we create the structure, to neatly like keep this array inside of this user structure. And we dynamically allocated it. So the point of showing this was to just show that it also works inside of this struct, okay? Arrays are same everywhere, even inside of the structures. Now, this next concept is going to be a little more advanced, and here, like, really, don't worry if you didn't cover structs yet, and if this is not going to be making sense. But whoever covered structs, I guess this is a useful thing for you guys. You can also dynamically allocate arrays for structures. So the same way you can do the pointers to the primitives, you can do pointers to the structures. Okay, so right now get ready for some spaghetti code. Okay, we're gonna create this time. So our type is user, and we're gonna create a a pointer to the user, and we're gonna call it our user. Right? We're gonna say our user equals malloc. How much we're gonna make it? Five, right? Let's do five again, or yeah, five is good. And then size off. Now question: size of what? User. Awesome. Does everybody else understand why this is user here? Because mind you, user is a new type that we created. It's not an integer, right? There's no convention size for that user, right? It's not like 4 bytes. It's going to be a custom number of bytes, and the compiler is only really going to know it from like looking into here, right? Since we sent it a size of user, it's going to see that, oh, okay, there's a type user in here, and that user type has 4 bytes here for the ID, and then some more bytes for this reference, right? Remember, this is just a pointer. This is not the array itself. Uh, this only stores like either 4 or 8 bytes because the address is in hexadecimal, right? The values in hexadecimal that we had, and these addresses they only take either like 4 or 8 bytes depending on the machine. So that's how the compiler comes here, calculates the size. So in our scenario, let's just say this is going to be 4 plus 8, a total of 12 bytes, and it's going to allocate. It's going to understand from that okay, we need to allocate 12 bytes for that. I'm not going to do 12 here. I'm not that risky. Okay, I'm not sure if that's going to work because we just assumed that in my machine the address size is 8. But what I'm going to do is I'm going to delegate that task to the compiler. He's going to decide what's the size of the user is. Okay, and we're going to allocate that way an array for our 5 users. Who wants to tell me what I'm doing now? Three. Okay, the same guy. Next time you don't tell. Okay, next time. I already know you learned it. What are we freeing? Not you. Not somebody else. Oh, sorry. You answered a lot. I believe you know it. Listen to you. No, no. Go. Our user. Awesome. One good way to test it, guys, in your codes, just count all the mallocs you're doing, count all the frees you're doing. 3. They all should match, okay? And if the mallocs are inside of your for loop, just watch out for that, right? Well, I don't think we did it yet, so we'll probably get to that. Oh, okay, we're just about to get to that. Okay, so yeah. Watch out for the number of mallocs. They have to be equal to the number of frees. And once again, uh, just to bring this point home, malloc and free, they're just tools that are given to us from this library right here to allocate and deallocate memory. Okay. All right. Our user. So we gave it size of 5. We freed it. Okay. So this is we just did our due diligence ahead of time. We freed it before, but now we can forget about it, right? Now we can play with this block of memory we just got, right? So we're gonna do a for loop to iterate through the 5 users that we now have. We're gonna keep abusing this variable I less than 5, I plus plus, and we're gonna say our user. So we remember this is pointers and arrays can be used interchangeably. If you gave the size, if you by the way, if you also gave it the size of 1, this would still could be treated as an array. It would just be a size of 1 array. Okay. In our case, it's a size of 5, so um, we're treating it as a regular array here, and we're gonna assign it to what now? So we're gonna say user app our user dot id. of the index I, right? So since this is the array of our users, we can still access uh, the elements of that user through dot. By the way, I don't think I mentioned it for those of you who don't really know structures like that. The way we access these attributes of our custom type is by using the dot operator. I think I definitely forgot to mention that. Okay, so user dot id. That's how we access the ID, the attribute named ID inside of this struct. Okay, and this is exactly what we're doing here. We're saying our user at the index I dot ID, right? We're accessing that structure and we're assigning it to, let's just assign it to, or sorry, to I. Now, each of these five users still do have this array of five friends, right? So now what we're going to be doing, this is going to be a little more interesting, that we're going to be allocating memory inside of the for loop. So there's going to be five mallocs inside of here, right? Because this loop runs five times. So the way to do it is we have our pointer variable inside of the structure, our user. What's the name of that pointer variable? Can someone remind me? Not you. It's the what's the pointer name? I'm gonna give you this hint. So here's the structure. What's the pointer name of what's the name of the pointer inside the structure? The friend ID list. Correct. Awesome. So we're gonna take that. We're gonna access that. So this is gonna be our storing place because, like we discussed earlier, pointers are a storing place for addresses, and this address is going to be returned to us through malloc. We're going to give it a size of 5 because we have 5 users, right, in the outer loop. And what here? Size of integer, right? Just because friends IDs are integers. And now this becomes our official array inside of the structure, inside of this array of structures, in each of these elements of these arrays. And here we can do another for loop. You guys probably covered nested for loops as well. Let's do 2 this time, all right? Just to keep it different with this outer 5. So now we have that each of our 5 users has 2 friends, and we're going to use a variable j for that because I is already used in this for loop. And we're going to say j plus plus each element of j. So our user, who wants to help me? Inside of here, what goes here? J? No. Remember, our user is our outer variable, right? Sorry, I is our outer thing. It's on the outside. So we use eyes to tell which user it is. So we're gonna say here, we're gonna say I. And friend, since friend ID list, we made it an array, right? By allocating it memory of 2 elements. We made an array. So now we're accessing it, we're also accessing an array. And this time my friend can help me. Now it's J, okay. So that's the strategy. Keep saying J, one time it's gonna work, right? All right, so J is gonna be assigned to, let's just say, let's say J times 5 this time. Or actually, let's give the same number to these, to all these, just to like tell the difference between these and these, right? Because these are also going to be 0 through 5 or 0 through 4. So we'll give this a 100, just a random variable, and they're all going to be same. Am I missing anything? To free, okay. What do I need to free? Right, okay. Where do I do it? Right here? Outside? Okay, so if I do it, you say I do it here, right? Because that's where the, because remember, I'm gonna do Control F, right, to search up all the mallocs I have. Malloc. Well, these mallocs really don't count, so I'll remove this. Okay. Control F malloc. There's probably also a free here. Yeah, I'll remove that as well. So we have 3 mallocs. We'll also have two frees. Oh, where does this new free has to go? Here. Okay, I'm gonna give everybody a hint. So the mallocs, there's actually this is actually inaccurate. It says here we have three mallocs, but in reality, how many we really have? Seven, right? Something close to that, because we have two outside, and this one really gets iterated five times, right? Because it's in the for loop. So we need to resimulate that condition that it's being done five times. How do we do that? Not you. Put it in a loop, in a different loop, right? Because if we put it in the same loop, we could do that, but like, what would be the point of creating it? We would want to like do something here, right? Something, and then we would want to free it at the end of a program, right? So we're gonna do it in a separate loop. I equals, we can remember, we it's a separate loop, so we can reuse the I, right? Just a reminder. I less than 5, right? So we still have 5 users here. And we're gonna do I plus plus. Awesome. Well, I already did this. All right, so here we're gonna do free our user dot friend list, right? Is that correct? Looks good to you? Are you sure? I. Where do I need to put the I? I'm definitely missing I. Our user. Here? Here, right? Awesome. Like this. Yes. Good job, guys. Good job. So since we're allocating for each our well, actually, now that we spoke about it, we're also missing it here. Okay, so this is not planned. This is me actually missing it here. So here it's really was supposed to be like this, because we still didn't print it. We didn't see that error message, but that would be an error message. So here we're actually doing, for each user, we're accessing the friend list of that user, and then we're allocating the memory for the array, so to make this an array. Okay, so we're free now, and now here we can do some fancy stuff, or or just like some useful stuff that we would normally do with this user. And what we're gonna do, as we've been doing all the time, we'll just print everything to prove the point that everything worked. We're gonna say printf id of user number g equals to this number, new line. First decimal is I, number index. Second one is our user I dot id. All right, just to prove that works. This prints, right? And now we need to run a nested for loop to access the friends of that user. J plus plus, our user I friend ID list. What goes here? J. Awesome. Use the J guy. We got a dedicated J guy. What are we missing? Printf, right? Percent, or rather, we're gonna do a couple. A one tap will be enough, and then print number percent z is gonna be percent z new line, right? And then there's gonna be J and I here. Awesome. All right. Make it smaller. Whoever's copying, feel free to copy. We're gonna run this and hopefully verify that each user got dynamically allocated two friends. Okay. By the way, those of you who want this code for reference, a cleaner version of that is going to be in our actual GitHub. So each of these concepts is going to be actually separated in its own like code file, right? For example, the simpler stuff that we covered in the beginning is going to be in one file, and so on and so forth, right? So just FYI, this will be also available. So yeah, this worked. Okay. Question: can we print it in a fancy way? Awesome. You guys are gonna help me. So let's take a look at this. Let's remember how it looks, right? So 0, 1. So the outer loop is 0, 1 through 5, or 1 through 4, and the inners are going to be 100 to 500. Okay, just remember, so that we verify that it looks the same with the outer with the fancy loop. Now we're going to comment out these. Oh, now we're alone. Let's do printf. So first off, the ID thing and like the text stays the same, right? ID user number D, new line. This stays the same. The thing that changes is this. Okay. Who wants to be my assistant? Well, our user, right? That's obvious. First, I'll just get that out of the way. I'll do the easy job for you guys. Our user. We have that. Okay. Where are we putting the I? The famous I. Plus I. Okay. Parentheses around it. Star at the front. Awesome. Because if I didn't do the star, what would it be? Somebody else, not you. You know. Or you don't know? Oh, okay. Guess. It would be, so dereferencing is the act of going from what to what? From address to the value that its address is storing, right? So hmm? Our user is a pointer. That is correct. Pointer star. If you take a look at our definition, or rather, it's here. You're going to notice that our user is a pointer. Yes, there's a star here. Why are we putting it here? Because oh sheesh. So I need to go back, right? Restarting the workshop. So pointer is a way to remember how we were the first thing literally we did, accessing the address of a variable, right? We have an int, we get its address with the ampersand. Pointer is a way to store that. So uh so point, where is that example, right? We create a pointer int pointer x, and we give that pointer the address of a. So the same thing we were doing here, right? The referencing the address. Remember, the dereference operator is applied on the address of the variable always. And the pointer stores the address. So we are it's legal to apply the dereference operator to whatever is storing the address. And now we're doing the plus I because we're treating it as an array. Technically, it's not an array. It doesn't say anywhere. It doesn't have like a birth certificate. It's not an array. We allocated 20 bytes because each element is 4 bytes, right? 5 elements in the array. We're treating it as an array. That's our little secret. And we are saying plus I, like plus 0. So that's first element. Plus 1, the next iteration, right? That's the second element. And each of these are the addresses, and we dereference them. This is how we get the actual value. Right? But when we dereference it, we get the user struct. What do we still need to do here? Dot .id. Awesome. This guy is impressive. We print this. For now, we'll just leave it empty. All right, so we made a mistake here. The thing we're missing is a parentheses around these because we're doing a dereference, but the compiler doesn't know that. We have to tell it, hey, this comes first, not the dot. Compiler without this compiler would think the dot first and then the dereference, right? But no, the dereference comes first. Run it. So the ID part is easy. ID part is easy. We just did this and that was enough. Now rewrite it. No, just kidding. Just kidding. Let's now do this. Okay. Let's now do this. This is gonna be some interesting stuff that you definitely would want to like show your friends to show off. All right, get ready. So misspelled here. Friend. Okay. So friend number, and this is gonna be the index, right? And then parentheses. Uh, the actual index of that friend. So the J is the same. I'm again doing the easy job for you. Array user is the same. Where are we putting the I? Where are we putting the I? I goes somewhere. It's minus I, right? Plus I. Thank you. Uh, we're still doing that, and we still need to dereference it, don't we? Okay. Life taught us that we also need parentheses around this. Dot. Louder. Friend. Awesome. ID list. Okay. Now this is in itself is a array, but we can't do this. We can't do this, right? We want to be fancy. This is the old way we did. If we did this, by the way, it will work. Let's do it. It works, but we couldn't live with that. Like we're fancy. What would we do? Rescue us. The J guy. Oh, the J guy is back. Plus J. Oh, sorry, J guy. The brackets. There you go. Wait, no. The brackets is the non-fancy way. You want to do the parentheses? Yeah, correct. So, where do parentheses go? Tell me. Where? After J. Okay. In the beginning, where? Here? No, very beginning. Awesome. Star where? Outside. Wow. This guy is good. Let's give the applause to. No, really. Impressive. Yeah, we need to cancel this workshop, man. He knows everything. Okay, so this is the fancy way to iterate through this friend list, right? A lot of nesting, a lot of accessing the attributes. For those of you guys, probably here actually in person, there's only one guy who really knows structures before this, right? From a different context. But for those of you watching, there is also a interesting notation that is worthwhile mentioning. I'm also mentioning it here in the slides, in the last slide. Let's get back to that. Instead of the dereference and then parentheses dot id, right? The C creators, they thought of this. They really knew that this is ugly, so they created a way to do the dereference and then dot operation in one step. And that's another notation you just guys have to remember, but not at this stage for some of you guys, because you guys want to focus on your midterm. You can just like not remember this, okay? If that makes sense. There's a arrow notation, right? Well, it looks like arrow, but it's like dash and then greater sign. Arrow notation. So this does two steps at a time. First step is the references, puts it in parentheses, and accesses the ID, right? As you can see, there's no star. This is being done by the arrow. Let's rewrite it that way. This time I won't take help from anybody because for now, like, don't worry about it. This is just a good reference for you guys. So first off, we're get rid of this. We're doing this, moving these. Okay, so this is not going to work. Let me rewrite it from the beginning. So our user plus I, and we're gonna have a step of dereferencing and accessing friend list at the same time. Friend ID. And then we're gonna have a plus J. So this actually has to be dereferenced. All right, there you go. A lot cleaner, right? Than this ugliness. But this is robust, okay? For now, if you don't want to worry about this notation, you know, this is good enough. Same applies here. This is going to be even prettier because here we just do an arrow, okay? We're going to also remove these, by the way. They're in the way still, right? How pretty is that, right? Okay. So we've reached the end of the slides, but these slides are actually missing one thing. And I'm going to explain this, and after that, we're going to see if you still guys have power for a couple examples, but it's a 7. We'll just wrap it up after this, okay? So there's one question that I was hoping I would hear from you guys. So we're doing malloc, right? Malloc really takes care of the scenario of when we don't know the size of what we're allocating ahead of times, right? But what if we know it, we allocate it, but then we want to do what? It changed, right? For example, the friend list is not going to stay the same, right? And from some of you guys who already know different programming languages like Python or like JavaScript, right? They do have these things that they call lists, right? We, the C people, we don't get that, right? The list is the we know the array. Array has a fixed size. We have to define it or allocate memory for it. Lists, we don't have to do the malloc things. That's the part of the reason everybody loves Python, right? For lists, we just add elements and it dynamically like takes care of the memory for us. But we still have to do this here because we allocate memory once. But what's good it's going to do if we cannot like change this, right? You see what I'm getting at? So we're going to have to know a way to reallocate the memory that we already have. And I'm going to just show it on an example of a regular array because uh, the user thing is redundant. Okay, it's going to be a lot of ugly code commented out. All right, we're going to create it my r. What am I missing? The star. And it's going to be, we're going to my r. What are we doing here? Malloc. All right, I'll not torture you no more. I'll just do this. Let's do 3 users. Size off, and then integer. Wait, free. Every allocation is accompanied by a deallocation or a free. And then let's imagine, or all right, let's populate it. Int I equals 0, I less than 3, I plus plus. Let's do it a regular way. All right, we're just in a little bit of a rush. So yeah, everything is allocated. To prove the point, we're just going to run another for loop and print everything. Okay, printf %t. All right, we got our 1 2, right? Because it's 0 1 2. Sorry. Now, at this point, after this line, after printing it, I want to make it not 3 but like 10. Okay. The function for that, and unfortunately this is not in the slides. I'm gonna edit the source code. At least the source code is gonna have it. But the function for that is similar to alloc. It's gonna be realloc. Okay. And what it's gonna take, realloc stands for reallocate, by the way. Pretty straightforward, right? What it's going to take is going to take the pointer of the previous thing that we're trying to allocate, right? But most importantly, it takes a pointer, my r, and then it takes the new size of what we want to reallocate it to. So since we had a size of 3 elements, now we want to do 10. What do we write in here? So 10, obviously, duh. Now what? Size of, awesome. Size of int. So now since we allocated extra couple elements, the C compiler is really smart enough to keep these. Like it's not gonna just like erase it with like random trash memory addresses. Okay, so if we rerun this print, only the new ones are gonna be trash addresses. Okay, the old ones are still gonna be there for us. Let's make a separation somewhere in here. So only so you see, after reallocating, we got more size, and we still preserved our previous elements. We just got some. Well, it's not trash here. Maybe this implementation of their website, because remember we're in the website, right? The actual C compiler might have given us some just from previous random address cells. But that's a useful thing to know, right? Realloc. For realloc, you don't need a free, right? Because you're not allocating any more memory. You're just the pointer which points to this block stays the same, and we're freeing it here. So you're only matching freeze with each malloc and not with realloc. That kind of makes sense, right? Because this is already the pointer, we're freeing here, but now it's just 10 instead of being 3 here, right? Questions from like any point, maybe some earlier stuff we thought. No. Okay. Yes, so we already went. We pretty much did a lot of examples throughout. So does everybody now kind of understand at least what's the purpose of pointers in C? It's not that scary, right? We're just taking address of the variable and using it to point to some other address, right? Raise your hand if you feel at least a little bit more comfortable with pointers. Okay, awesome. Good job. All right, thank you guys. Thank you for attending. I'm gonna share the QR for this thing. So this is gonna be a questionnaire for you guys. I'm honestly not sure what it's gonna be, so I'll just let you guys see it. And in the end of that, is there's probably going to be an access to the slides. Uh, and yeah, that was it.
I had a
Oh,
question.
you had a question. Sorry, go.
RV, you know what RV, right? RV.
Arc
Yeah, our teacher puts it in the int main.
int main.
Yeah, the main function. He puts argc and argv.
Arc those are the command line arguments, and this is applicable when you're running C program from your like actual computer. We were running it from the website. If I went to my like C actual like VS Code, right, and stuff like that, I would be able to type GCC like compile whatever C, and then when I have a compiled version of it, I call it with like a second string, right? So for example, my compiled output file is called a.out. I call a.out, and then I give it a second like number. Let's say the 5, and this is what goes into argv argc.
Yeah, you know how it is double pointer, right?
Double pointer. Oh, exactly.
Yeah,
Yes.
car double pointer. So
Let me show that. Let me
the
show that.
arg the argv points to the address, which points to the string, which points to the characters.
So it looks something. I think char double pointer arg
It's int argc comma car double pointer
int
argv.
goes first, right?
Yeah, int argc
Argc and
comma
then
car argv.
argv. Okay,
Yeah.
so argc stands for argument count, how many arguments you have, and argv stands for argument vector. This
So
is
I know what they do, but I was wondering how it actually works. The
okay.
RGB
So this is
vector.
not going to work because we're not calling it from here. I'll just move them inside here if you don't mind. Okay, I'll do like this and I'll show you. I'll for now comment out all of this except for return 0. That's a good question, by the way. That's like a real life example of let's say we have 5 arguments. Let's say we have a character array argv. Actually, sorry, I shouldn't call it a character. It's a pointer to a character. So the way we well, the way it's going to be given to us is it's already going to be printed to something, but here we're just going to mimic that by actually feeding it something. Okay, so here I'm just going to make a for loop. I'm going to say, or actually, yes, I'm going to say a for loop int I equals 0, I less than 5, I plus plus. And what I'm going to do is, well, 5, I'm saying 5. This really should be arc count. And here for each of these arc v's, all right, this is just a double pointer, which means it's a pointer to a pointer. So I'm going to say arc v. Let's do it a fancy way, right? Plus I dereference. Now this is a string, and we're gonna do. So what we're gonna do is we're gonna say this, if I remember correctly, equals m alloc. Let's do like let's do 10 times size of. Help me out. Size of what?
So,
String. There is no string in C. Watch out. Char, right? Character.
So that's how to make a string.
That's a fancy way, quote unquote, to make a string, yes. But if you're making a string this way, nobody's gonna blame you.
I like to make a string.
Yeah. So, because strings in C are arrays of characters, right?
Yeah.
So this, or actually, sorry, not like this.
you said it's a pointer pointing to a pointer which is pointing to characters, right?
Yes, and
The middle pointer is actually a string because
well,
it's
yes, we call it string, but it's really a array of characters,
it's
right?
an array of
We call it string, but in C there's no such thing as string. So this is a pointer to a pointer to a character. That means it's a, we can tell it's a array of strings. Okay, I'm gonna get to it. I'm almost done. So let me remove this. So we're gonna allocate this to that, and we're gonna say, all right, let's first take care of the deallocation, right? Uh, so we're gonna say free this, all right? And let's see if this runs. Awesome. Turn 0. So now we're allocating a block of memory, and then for int j equals 0, j less than 10. Since we're allocating 10, j plus plus. This is going to be a pointer to a character, and we're going to say arg v plus I. Now this is a pointer to a character. Plus j. We're just gonna make everything C, okay? Just for this example purposes. So all of our strings are gonna be C, 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 C. And this doesn't happen in real program. We're just given the result of this. Like, well, actually it's in the command line, right? We're gonna say, this is gonna be a commented out, okay? We're gonna say, first we're gonna do gcc, right? Like test.c, right? And as a result, what we're going to get is an executable file, a.out. And the way we call it is by doing like this, right? Is that the way that you do it, right? And then we give it, like, for example, c, and then we do it 5 times. So this is what we're imitating here, okay? So to print that, I'll actually make it below. For int I equals 0, I less than arc C. Well, this is actually how you do it in your program, I plus plus. And then printf. Remind me, guys, how do we print strings? Percent %s, right? This is just a C thing, there's no data type string, but we can still leverage this by doing this. And we're going to say arg v sub I. Oh, did I not allocate? What is wrong here? Troubleshooting, live. Ooh, nothing happens. Oh, rookie mistake. Still doesn't work. Well, probably JJJ, I. Hmm. Okay, bear with me. Here, let's just do some testing. Oh, interesting. Nothing prints.
I did a pretty simple question. Like, it's just a simple, specific question. You know how when you call the zero index with argv, it
Uh huh.
gives you it gives you the first argument that you type
Yeah,
in.
in reality, it really looks like this.
So,
So
what can you call to make it print out all the arguments all at once? Like how string works, it prints out all the characters all at once to make a word. How do you What do you call to make it print all the arguments all at once?
you
Like a
call
string,
printf
or
and then like this, that s for the string, and then you pass in the address of the first element, which is like we discussed before, is the address
but
of the.
for strings too, you don't have to do it.
You don't have to do that for strings. Wait. All right.
Arg zero, arg v zero, it prints out one of the arguments, which is a string,
Yeah,
right?
well, but you're doing arg0, right? That's why you're only printing one. If you do arg1, if there is a second one, you're going to print the second one.
Yeah, but it's when you do arg zero, it prints the word, like it prints an array. The word is an array, right? So
Yes.
it prints the array all at once when you do arg zero. Is there a way to do it with
Oh, one by one, you mean? Or all of the five of them?
all five of them?
Well, you have to do a for loop.
For loop,
For
but
loop.
for arg zero, it is required for loop, right?
Because it's the first element. You're printing one of them.
But the element is an array.
Yes. Can you draw it on the board?
On the board.
Or
So how do you print argv as an element, I guess?
argv as an element? Well,
Yeah,
argv is an array.
but string is also an array, but we printed it as an element, right?
Yeah.
So can we do it with this array to print it as an element?
Like character by character, you mean?
Just like the whole thing.
The
Like
whole thing?
the how string is an array, right? It's an array of letters, and we
Yes.
print it all at once.
Oh, okay. Now I understand your question. There's no way to do that. There's only for loop.
There's no way
You,
to do
you,
it.
you only have to do it through a for
But
loop.
with strings you can do it.
But with strings, you can, because string is just a special case. The creators of C kind of like foresaw this, that strings are, arrays of characters are most of the time used like together.
I see.
So
So
that's why.
array of characters you can print them all at once, but array of arguments you can't do it. There's no
Yes, you
way
can
to
do it. Yeah.
I was kind of
So,
getting
for example, yeah, like if I have char uh, char r, and then it's an array of three characters, right? Let's just, for example, say A, B, C, right? We're just gonna do this, and then if I do printf, so we comment out. It's just like make sure we delete, because there are some frees and allocs here that we don't want. Awesome. And then if I printf percent %s new line char array. What? Oh, we still have the. All right. Okay. Good catch. So we get an ABC, right? But this is only because this is a special case. There's a S thing, right? And this, in reality, what this is a address of the first element. So this is also a still a pointer. Still does the same thing, but it only works because string is a special thing. If we do int array, it's not going to work. Because integers, they don't have the special type, right? Like chars do. If you want to print one character, you do C, right? But they have a special the notion for strings S. But for the other arrays, there isn't such thing. There is only a D, and this is going to fortunately just give you a warning and print you the address of that. And really, the word for that would be P here for pointer. So for other arrays, you cannot print them like that. You have to do a for loop in C. In Python, you can. I think there's, or in Java, stuff like that. There's a way. Unfortunately.
One question on the previous loops that you were doing, it was creating like a char pointer to other char pointers.
Yes,
which
so it
they
was a
pointed
double
for
pointer.
character.
Say it again?
So it was like a main char pointer that pointed many char pointers, which pointed each one to their character. Just like that.
Yes, it was a double pointer character,
Yeah,
and the outer pointer is for
like the main one.
the main one. That's for like the strings. You can think of it as a array of strings,
Yeah.
and strings in itself are also arrays. So it's an array of characters.
Yeah.
That's why it's like char, double pointer, array to pointer to a pointer,
Okay.
double array. Confusing, but yeah. All right, awesome question.
I have a question. It's not with pointers though. It's with Git.
Git,
I was using it for the first time at the hackathon,
awesome.
and
Yeah.
when I was like trying to use it, and I accidentally like, I think put all my folders or like all my files, like they're all like green, like they're tracked in ES4
Okay.
or untracked.
Uh-huh.
How do I like?
So let me quickly stop recording since it's not a C pointer question. Thank you everybody for attention. We're gonna stop.